In the previous video, we talked about the structure of a generalized linear model. The reason we discussed it is because what we are really going to be predicting for is for a categorical variable, more specifically for a binary variable of success and failure. When we have binary data, technically it has a distribution called the Bernoulli distribution. Some of you may have heard of the Bernoulli distribution before, but those that have not, it's a binomial distribution where you only have one trial. So for example, I am going to flip a coin one time and I want to figure out if it's going to be heads or tails. Or I'm going to kick one field goal, I want to figure out if it's going to be a success or a failure. So just a single trial, we would like to model this distribution. So first, to understand why we're going to model it the way that we will, let's talk about actually calculating the probability then that y were to take on a certain value. Well, the only options actually for y is either going to be 0 successes or 1 success because there's only one trial. And if we look at the binomial distribution with an n equal to 1, it's just going to turn out to be pi raised to the y power times 1 minus pi raised to the 1 minus y power. So as you can notice, if y is 0, this will disappear, this will become 1, and I'll just get 1 minus pi, which is the probability of failure. And if y equals 1, I'll get pi to the first, or just pi, times this will just turn out to be 1. So I'm either going to get pi or 1 minus pi as my probability, depending upon if it is a success or a failure. With this Bernoulli distribution, and using the idea of the binomial distribution, my expected value of y is just going to be pi. So if I have a 50% chance of heads and I'm going to flip the coin once, I expect half a head. The variance of y for this Bernoulli distribution is pi times 1 minus pi. So our goal here is to find a generalized linear model to model pi at specific values for this explanatory variable, or variables, depending upon how many we have. So let's start by looking through an example of what I would mean by this. So suppose that I wanted to estimate the probability of success, pi, for a field goal. So we're going to kick a field goal, and I want to figure out my probability of making that field goal. The value of pi will probably be different depending upon the distance the attempt is from. So if the kicker is kicking from a 20 yards out versus 50 yards out, we probably believe that this probability of success will be different. So our explanatory variable that we're talking about here is that distance of the kick. So how I might want to write this is that pi is going to be a function of x. I'm going to call this pi of x. This will represent the probability of success when my x is equal to whatever little x happens to be. So 20 yards or 50 yards, I would plug that in. Right now, we're just going to focus on having one explanatory variable. Here, that would be our distance. We will get to where we actually have more than one, but again, just for understanding first, let's just start with one. So let's talk about a linear probability model and what would be the actual problems with this. So if I just were to do just good old ordinary regression on this, and not try to use a generalized linear model, what I would say then is that my expected value of y, which in our case is just our pi, would just be our intercept plus our slope times our explanatory variable. And we would also be making that assumption that y is distributed normally with a mean of mu and variance sigma squared, In our case specifically here, mu would be the same thing as pi. Now, what are the problems with doing this? Well, the first big one. This is already in violation of our distributional assumption for y. Why? Because I know it has this Bernoulli distribution, or a very special case of the binomial distribution. So as soon as I'm putting this normal model on it, that automatically violates what I already know to be true. So we technically know y is this Bernoulli distribution. Right, here's also some problems. If I look at this model, it doesn't really force anything to happen. Let me first make sure I go back up here and fix that this pi should be pi of x, just so that we're all on the same page there. So what it would allow for is this would technically allow that this pi of x could go negative on me. There's no restriction put on there, so I could have values less than 0 pop up, or I could have these values end up being greater than 1. There's nothing restricting that from happening. Now, why is that a problem? Well, if pi is our probability of success when x is x, our probability can't be negative and our probability cannot be bigger than 1. So this is a very big problem. Finally, our last big problem with this model assumption would be that this actually assumes that we have constant variance. We had that assumption up here when we put in this sigma squared up here, right? There's just this one variance. It does not change. And that's been a pretty standard assumption most of the time when you've probably done a model. But technically, I know that ours changes as a function of x. How do I know that? Well, I know from above up here that my variance is pi times 1 minus pi. So for us, technically then, our variance of y is going to be this pi of x times 1 minus pi of x. So since I know this is actually a function of x, it's not going to be a constant variance. It's going to depend upon my level of x. So what's the moral right now? We're not going to use this model. Right, that's our big takeaway right now. So what model can we use instead? The most common one used is what's called the logistic regression model. So this goes back to that logit link function that we discussed in the previous video. So now our mu is just the same thing as pi. So if I take this log, remember log is our natural log, of pi of x over 1 minus pi of x. Again, refreshing that back to last video. We had this function here, so that's what we're working with. So mu is the same thing as pi of x for us here. I'm going to let that be my alpha plus beta x. And so then when I actually take this and I solve this back for pi, I get that pi of x is e to the alpha plus beta x over 1 plus e to the alpha plus beta x. So why is this so much better? Well, if I look at this, the bottom is exactly 1 bigger than what's ever on the top. So I definitely know that this will be less than or equal to 1. It can never get to be bigger than 1. It can really only ever actually approach 1. It's actually really never even going to equal 1. But I definitely know that it's going to be a valid probability on the positive side. Now, do I know that it can't go negative? Yes, I know that because e raised to any power is going to always give me some type of positive number. So I know that this now has to be between 0 and 1. And that's definitely what I needed. So let's talk about what this graph actually looks like to understand how this is very different than a regular regression model. So this is not pertaining to any specific contextual example. This is just to get a plot of what it might look like. So if my alpha coefficient is 1 and my beta coefficient is 0.5, and I were to model this function we have up here, my values of x are on my x-axis, and I'm modeling that pi, that probability of success, this is what it'll look like. So you'll notice that it approaches 0. It's never going to go negative, and it approaches 1, but it can never go above it. And we see this S-looking curve. And so that's what a logistic regression model is going to look like. How spread out it might be different, but it's going to have this idea of this S-curve shape. So it's no longer this straight line model that maybe we're used to. It's not even like a quadratic that we might be used to. How I would actually use this is a logistic model. Okay, what would happen if I changed my beta coefficient? If all I did was make my beta coefficient now negative 0.5 instead of positive 0.5, you're going to see a very similar S-shaped curve, still bounded between 0 and 1. But now we're seeing still sort of like this negative trend. So let's actually make these notes down here where you have room. Okay, so what I see then is when my beta, that slope coefficient, is positive, there is a positive relationship between x and pi of x. So as x gets bigger, my probability of success is also going up. Going back to this curve, right? So as x gets bigger, my probability of success increases, but again, can never go past 1. Now when that beta is actually less than 0, which with what we have up here, we're seeing that opposite relationship. So when beta is less than 0, there is a negative relationship between x and pi of x. So here's what you're going to hear me call beta. And again, since you're not seeing me say this, I want to make sure I emphasize it. You're going to hear me call beta with quotes around it the slope coefficient. So again, the big reason why there's quotes around this slope, right? It's not a straight line relationship, so it's not technically a slope. But even though it's not a real slope of what we think about with an actual line, it's still giving me the same idea of this directional relationship between my x and my pi of x. So even though, again, it's not a true slope, it's giving me a similar idea of the relationship when I have talked about a slope in the past. Another thing about this is the shape of this graph is actually symmetric. About pi equals 0.5. Now explaining what I mean by that here. So if I go back up here on my graph and I look at where pi equals 0.5, so pi of 0.5 is around here. So going across there, that kind of happens about right here on my graph. So if you can imagine taking, let's see, I'll do this in green, this piece. So if I were kind of to rotate that piece up 90 degrees, it's going to perfectly overlay on top of that piece. So that's what we mean by symmetric, is that very similar trend as I go away from 0.5 is doing the same thing, just in that opposite direction. So you just spin the one piece, it would be on top of the other. That would also be true on our other picture here as well. If I find that 0.5, the one piece, if I swung it that 180 degrees, it would fit on top of the other piece. All right, and finally, we already stated this once, but it's good to go maybe ahead and have it here so it's all in one place together. Another great thing about this is that as soon as I've now given this logistic regression model, I am now guaranteed that my probability of success, even as a function of x, is still going to be between 0 and 1, and that is what we need. All right, finally, let me go back up to my R code here. So this R code was just what I did to create. This is what would be the first plot, since my beta is 0.5. How I actually function the pi so that you can actually see this pi of x formula typed out into our code is all we're doing there. And so it's just creating those plots. To get the other one, I would just change that beta to be negative 0.5. So let me show you that code real quick. So that'll be the very first part of my code here. So if I just run this first set of code, you notice how it gives me very, very tiny here, so I can make my picture bigger. So then my graph there will kind of grow with it. When you want to, of course, do this, you can export it as an image if you would like. I have this snipping tool where I can just actually come over here and kind of just take a quick little picture of what I'm looking at, and I can copy and paste things over that way. So there's different ways of getting this graph into whatever document that you might be trying to give me as well. I'm talking a little bit more about the actual code here of creating the graph. So this plotting type, this S just means it's going to do it as a square here for me. So I'm actually just going to kind of run one line of code at a time here for you. So it's going to give me a plotting of a square. This first part will just give me the actual plot. So on X, it's going to plot what actually I have up here for X. It's going to plot Y as my pi that I just did the calculation of. X lab just means the X label, so what I actually want written down here on my axis. Y lab is what I want written for the Y axis over here. My limits of Y, I want between 0 and 1, so that's where the 0 to 1 came from. Notice I didn't specify X. By default, X is going to go from that negative 15 to 15, since that's where X was. Type, I just want a line. This is for a color, so 2 happens to be a red color. You can play with the different colors, or you can always Google to kind of find our color codes for plots if you want to find something more exciting. And then finally, this grid line, when I run it, is actually going to put those dotted lines that you see on here. So I'm just putting some gray, and then the line type here is dotted for that one. So that's just how I created those plots. And again, if I just want to get that other plot, I'll just change this to negative 0.5. Notice how that feels like it looks a little weird because we already had the one dash in there for the arrow. But so I just have that extra dash in there for my negative. And then running it, we'll get the other graph that we had. Okay. So in the next video, we will actually start talking about, well, how do I now, for a real example, get estimates of alpha and beta. So we're going to talk about how to estimate alpha, beta, as well as do it for our first example.